Hey guys, hope you're all doing good and welcome to a new video. When the geometry of the battery pack gets very complex, it's going to be extremely hard and sometimes impossible to derive an analytical model, right? So in this scenario, the only way to achieve a solution is by using numerical techniques. We can use numerical methods. We can employ numerical methods and discretize the entire domain so that we are not solving the original differential equations, but we are rather solving a much more simplified linearized set of equations. This entire process is called as discretization, and there are several techniques called as finite difference method, finite element method, and finite volume method to solve differential equations. Right now, when applied to fluid flow, the most common discretization technique by choice is finite volume method. And computational fluid dynamics is all about solving discretized equations that have been derived using finite volume method on computers. Alright, so let's learn more about fundamentals of CFD. I have a presentation for it, and towards the end of this lecture I'll be showing you how you can build your own CFD solver using Microsoft Excel. It's a fairly simple solver, but I think you'll be able to understand a whole lot about CFD through this particular calculator. Alright, so let's get started. Alright guys, so in this video we will primarily be learning about what is computational fluid dynamics and also try to understand the math behind CFD. So what is CFD? CFD is a computational technique that's used to simulate fluid flows using a computer. Now if you Google Blender animations on YouTube, you will see a lot of cool animations like the one that I'm actually showing on screen. So this particular video was made by the Blast Raider YouTube channel, and you can see that it features a lot of really cool looking smoke animations, liquid animations, and essentially animations of fluids. So this is what you call as computational fluid dynamics. Now these animations are not made very accurately from a physics point of view. They are made accurately from a visual point of view. So it has to look correct. Doesn't mean that it's actually solving the right equations with the right amount of accuracy. Now in the context of CFD, you can simulate both liquids and gases, and towards the end of the video you will actually see that you can co-simulate fluids and solids together to simulate some really interesting applications. Now if you have never heard of CFD, I want you to think about electromechanical systems that you might have encountered in your academic or professional life and figure out how CFD would be useful for that particular system. Right now I actually have the answer to this question in the next slide, so if you want, feel free to just pause the video and think about it for 5 to 10 seconds. It turns out that anywhere fluid actually flows, you can actually use CFD to optimize the system if you really care about the system. In the context of electric vehicles, you might be interested in simulating the flow over the battery pack to make sure that the batteries are cooled efficiently. In the context of IC engines, you might want to see how the air actually flows through the intake port of an internal combustion engine and calculate things like volumetric efficiency. In the context of safety related simulation, you can basically simulate how fire spreads in a room, and the examples can keep on going on. Right, so anywhere there is fluid, which is liquid or air, involved, and if it is an engineering system that needs to be optimized, you can definitely use computational fluid dynamics for it. So now the obvious question is, how can a computer do all of these cool simulations? Well, I can give you a short answer, which is computers are very good at solving linear equations, and you might come back to me saying, so what? Well, what I'm trying to say is, if you give the right set of equations, right set of linear equations to the computer will actually solve it for you. And let's kind of take a simple example. So this right here is a common IQ test. Say that you're going to a shop and you're purchasing a packet of milk and coffee, and together the cost is $1.10. Secondly, the cost of milk is $1 more than the cost of coffee. If I say these two statements to you and ask you to find out what the cost of milk and cost of coffee is, you can immediately say, well, the cost of coffee is 10 cents and the cost of milk is $1, right? So the total is $1.10. And this is the answer that 90% of you will give. But that answer is actually wrong, because though it meets the first constraint, the second constraint is not met. If you say that coffee is 10 cents and the cost of milk is $1, together it adds up, yes, $1.10. But the cost of milk packet is not $1 more, it's just 90 cents more. In other words, this problem had to be broken down into two equations, right? So the first equation is the cost of milk plus cost of coffee is $1.10. The cost of milk minus cost of coffee is $1, because the cost of milk is $1 more than the cost of coffee, right? I hope that makes sense. Now, human beings are very intelligent. We can convert English statements into equations in our head, and we are somehow able to solve it. The thing that a computer can do really well is solve these two equations. If you give it the linear equations, yes, the computer can actually do it very well. The only thing that the computer cannot do is it cannot take a problem statement, a generic problem statement, and convert it into linear equations. And maybe someday computers would be able to do it, and if they're able to do it, I think that would be really amazing, right? But the challenge here is, for this simple problem, we can figure out what the equation is and we can let the computer know, hey, solve these equations for us. But for simulating fluid flow, right, what is the equation that we need to basically take, that we need to solve? So for complex simulations like this, what is the equation that needs to be solved? Well, it turns out that the answer is a set of complex looking partial differential equations. These are what you call as governing equations, and at the end of the day, the governing equations have been derived by simple principles like mass conservation, momentum conservation, and energy conservation. So here you have a set of partial differential equations, right? For example, the continuity equation states that the mass is conserved, right? This is the mathematical representation of the statement mass is conserved. Similarly, the mathematical statement which represents momentum is conserved is this equation for the x momentum, this equation for the y momentum, and this equation for the z momentum. The reason why you have three equations is because momentum is a vector quantity, and momentum would be balanced along x, along y, and along z. Finally, you have the energy equation, which basically says that energy can neither be created nor be destroyed. So now the challenge is, how do you take these equations and convert it into linear equations? Well, the short answer is discretization. For example, if you have a continuous variable such as dy by dx, you can convert it into discrete representation. Dy by dx is nothing but change, right? You can take dy by dx, which is differential change, and you can convert that into algebraic change or algebraic difference by writing it as y2 minus y1. Sorry, there's a typo. This should be y1. You can write it as y2 minus y1 divided by x2 minus x1. Now if you think about it, your Navier-Stokes equation consists of terms such as d rho by dt, d by dx of rho u, d by dz of rho w, and so on. So if we are able to write algebraic approximations for each of these terms, then we will be getting our set of linear equations. So let's do it for one term. So let's assume that we have a function, right? So this red line represents a function with respect to x. So these are 2 points of interest where the value of the function is f1, and here the value of function is f2. Now the x location at which the function value is f1 is called as x1, and similarly at x2 the function value is f2. Now if I try to compute the slope, which is also called as a tangent, it's going to look something like this, right? So how do I compute the slope for it? Well, I can just evaluate the value for dy by dx. So that is one thing. Now say that the quantity f1 is already known. If you know the value of a function at a particular location, how would you determine the value of the function at a different location? Well, this is where we can employ Taylor series. We know that f2 is equal to f1 plus df1 by dx plus some constant time d square f1 by dx square plus some constant time d cube f1 by dx cube, and so on. So here if delta x tends to 0, I can ignore the higher order terms, and looks like I made a typo. I forgot the dx term, so I've included that. We get this expression, and if I move f1 to my left hand side, I basically get the equation f2 minus f1 is dx times df1 by dx. Now if I take dx to the denominator of the left hand side, I have f2 minus f1 by dx is equal to df1 by dx. And there you go. This is basically an approximate equation which takes differential change and converts that into algebraic difference. Now the reason why I called this as an approximate equation is because we ignored the higher order terms. So these two quantities are not exactly equal, they are only approximately equal. But in the process of deriving that approximate equation, we have converted the differential equation into a linear equation. Now just to rearrange it, I can basically say df1 by dx is equal to f2 minus f1 by x2 minus x1. Now this right here is a linear equation, and a computer is going to be very happy to solve it. So what are the steps in CFD? Well, the first thing is you have to discretize the equation. In the previous example, we showed you finite difference method. In addition to this, there are finite element methods and finite volume methods that can be used to derive discretized equations, which would essentially be linear equations. The second thing is to discretize your domain. So this is where you split the domains into either nodes, elements, or volumes. And this is also called as creating a mesh. Once you have done that, you can solve the linear equations. Now these are the three things that a computer can help you with. You can either use a software package like Ansys, or you can write your own computer programs using programming languages such as C or C++. So once you have done that, analyzing the results, getting the data for engineering from the results, performing any design changes or validation, and if the design is good, communicating that to the product development team and moving on to the next problem, right? All these things are done by the engineer. So you need to understand that CFD would be a great tool, but if you don't have knowledge regarding a particular application, then you might not know what to do with the CFD software or the CFD program that you might have. So we have talked about governing equations, we have talked about discretization. Is that all there is to CFD? Now it turns out that in order to capture certain important key physical aspects that occurs in real life, you have to solve more equations. For example, to capture the effects of turbulence, typically a turbulence model is used. A turbulence model is nothing but a set of equations that govern the conservation of quantities called as turbulent kinetic energy and turbulent dissipation. If you have these equations, they would also be part of your governing equations, and when you solve it, you can basically look at the effect of turbulence. Similarly, if you want to simulate combustion, you basically need to solve an equation for that, which is called as the species transport equation. Similarly, if you want to look at the effect of fluids and structures together, you need to solve Newton's second law on the structural side to basically get the solid, to basically get the motion of the rigid body, and couple it with your fluid solver. If you want to capture the heat transfer on the solid side and the fluid flow on the liquid side, you basically do something called as conjugate heat transfer simulation. So this is where the liquid side is going to basically help you get the convective heat transfer part, and the solid side is going to be used to capture the effect of conduction, right? So in other words, in CFD, in order to capture a particular physics, you have to always make sure that you have the right equation. With just mass, momentum and energy, you can just perform fluid simulations. If you want to capture solid heat transfer, then you need an equation for that. If you want to capture turbulence, you need equations for that. If you want to simulate sprays, you need equations for that. If you want to simulate combustion, you need equations for that. So this is an important step that you need to remember, especially if you are beginning with CFD. You always start with the question, hey, what is the physics that I'm trying to capture? And then for each of the individual physics that you're trying to capture, you have to figure out what is the equation that needs to be solved. Once you have that set of equations, you then go ahead and set up the required parameters for that particular equation. Finally, you would need something called as boundary condition, which basically tells the computer what are the values at the boundary of the computational domain. This is very important to get an unique solution, because at the end of the day, you are solving differential equations. In order to get an unique solution, you need to basically provide the boundary conditions and also the initial conditions. The number of boundary conditions obviously depends upon the number of equations that you're solving. In addition to this, there are things like steady simulations and transient simulations. Steady simulation is where things are not going to change with respect to time, so the time derivative is essentially 0. Or you can perform transient simulations if you're interested in capturing the effect of time on a particular variable. Alright, so now let's build our own simplified CFD solver. So here, this is the governing equation that we are starting with. Now you can see that this equation is very similar to what we had in our one-dimensional steady state heat equation. In the one-dimensional equation, we just had d square t by dx square is equal to 0. In two dimension, you just have another term to capture the curvature or the second order derivative in the y direction. So this right here is the equation. Alright, so now what you can do is you can take these two terms and you can convert that into a linear form and then solve it using a computer. So let's basically take a look at how this is done. Now this is my original differential equation. So what I'm going to do is I'm going to use Taylor series first, right? So for example, what does Taylor series do? Well, if you know the value of, say, the temperature at a particular location, say x, you can actually figure out what is the temperature in the neighboring location, which you can call as x plus delta x. And similarly, you can use that temperature to estimate the temperature value at x minus delta x. Right, so here the temperature would be T x minus delta x, and here the temperature would be T x plus delta x. And at this point, this is temperature at x. So T at x plus delta x. So what is it going to be? Well, it's going to be T at x plus dt by dx measured at x multiplied by delta x plus dou square t by dou x square computed at x delta x square by 2 factorial plus dou cube t by dou x cube at x delta x cube by 3 factorial and so on. Similarly, t at x minus delta x is going to be tx, and the alternating terms are going to be negative, plus dou square t by dou x square delta x square by 2 factorial, and then minus, we essentially have the same term. Now what I want to do is, if I can call this as equation number 1 and this is equation number 2, I want you to add this. So when you add it, you basically get tx plus delta x plus t at x minus delta x is equal to 2 times tx, and these two terms are going to cancel out, plus 2 times dou square t by dou x square into delta x square by 2 factorial. Plus you have all the higher order terms, right? So now what I'll do is I'll just ignore my higher order terms, and what I can do is I can just simplify this a bit. So this 2 and 2 factorial can cancel out each other. So I have tx plus delta x plus tx minus delta x, and if I move this 2 delta x to the left hand side, I have minus 2 times minus 2 tx, and this is going to be equal to dou square t by dou x square times delta x square. So I can simplify this further. I can just say tx plus delta x minus 2tx plus tx minus delta x divided by delta x square, and this right here is dou square t by dou x square. Now this is an approximate equation because we obtained it by neglecting some terms. Now I'm just going to simplify this equation a bit more so that it's easy to remember. So if you remember, x is basically the center point and x plus dx is the point on the right hand side. So if I go to the graph here, you can see that if this is your point at which you're looking at temperature. This is the right hand side point and this is the left hand side point, right? So I can basically say that this right here is T right minus 2 Tp plus T left by delta x square. And this is going to be d square T by dx square. Now you can kind of use the same concept to derive d square T by dy square, and the result is going to be T top minus 2 Tp plus T bottom by delta y square. Right? If we add this, we get our original differential equation, right? So I'm going to say that T right minus 2 Tp plus TL by delta x square plus T top minus 2 Tp plus T bottom divided by delta y square is equal to dou square T by dou x square plus dou square T by dou y square. And if you look at the original governing equation, we know that this term is equal to 0. And the other assumption that I'm going to make is I'm going to say that delta x is equal to delta y. So what I can basically do is I can say that delta x square is equal to delta y square, and I'm just going to call both of them as delta x square. So Tr minus 2 Tp plus TL plus T top minus 2 Tp plus T bottom divided by delta x square equal to 0. So if you simplify this, you would get T right plus T left plus T top plus T bottom divided by delta x square is equal to 0, and then you have minus 4 Tp in the numerator. I can take delta x square to the other side and it becomes 0. So essentially I will have Tr plus TL plus Tt plus Tb is equal to 4 times Tp which means that T at point is equal to Tr plus T left plus T top plus T bottom divided by 4. And this right here is my governing equation. And you can see that that is what I have done. So alright, so now that we know what the governing equation is, what the discretized equation is, how do we actually simulate this problem? So this is where I wanted to introduce a simple tool for you. So this is essentially a CFD solver that's built on Excel. So what I've actually done is I've basically taken my rectangle and I've divided my rectangle individual cells. So each and every element here is a cell, and this right here is basically what you call as a discretized domain. In the real world, this could be a rectangular plate, it could mean anything. But here we are dividing the rectangular plate into individual volumes or elements, right? And inside each and every element, there is just one value of temperature, right? Though this element is big, the temperature value does not change. You just have one value of temperature. And you can see that certain cells in our mesh are colored in gray. So these are your boundary conditions. Your boundary conditions do not change. And you can see that for all the cells that are actually in the inside of our mesh, there is a starting value. And this starting value basically dictates the initial conditions. Now if you basically look at any of this particular cell, let's take this cell. If you look at the formula, right, the value at that center point is equal to value in the left hand side, top, right and bottom summed together divided by 4, which is exactly the linear equation that we derived. And you can look at any of the nodes that are on the interior. If you just double click on it, you can see that the value at this point is equal to the value at the left hand side cell, which is G10, plus value in the top cell, which is H9, plus value in the right hand side, which is I11, and I10, and then the value of the cell in the bottom, which is going to be H11. Alright, and this right here is what you would do in CFD. In this case, the domain is very simple, it's rectangular. But if you take a battery pack, the geometry is going to be much more complex. So for example, what's going to happen if the top boundary condition is changed to 900? So when I change to 900, you can see that the values are all changing. So I'm iteratively solving the temperature in all the nodes so that we basically get the condition that temperature at each point is the sum of all temperatures in the neighbors divided by 4. And you can see that the boundary conditions do not change. They are always the same. The corner points can be ignored. It really doesn't matter what you put in the corner because that's not used into the calculation at all, because if you look at this cell, it uses only the top, right and bottom points. It does not include the top, right and corner point. So we are okay. And you can see that the moment I change the value from 300 to 900, I'm getting a graph which basically shows the variation. And this is what you would call as post-processing. So whenever you do CFD, you basically start with discretized equation, then you discretize the domain, you have an equation, governing equation that you want to solve, and then you have boundary conditions. Then you post-process the results. But the other key part of post-processing is understanding what we are trying to say here. Though I'm seeing a bunch of numbers, it really doesn't mean anything. So what I'm going to do right now is I'm going to introduce a color map. I'm going to click on format and I'm going to select conditional formatting. I'm going to go to color scale, and what I'm going to do is I'm just going to click on this guy and I'm going to apply this color scaling. Immediately you can see that there are some nice colors. I'll explain what those colors mean. I'm going to say that if it is 300 Kelvin, the color should be green, and if it's 500, it should be yellow, and if the temperature is say 900, it should be red. And you can immediately see how heat transfer takes place in this particular case. The top domain, the top of your rectangular plate is heated up, and you can see that the temperature values are very high. And what you can do is with this simple calculator, you can do a lot more changes now. I can now change the temperature of the right side boundary, right? So let us change that to 500 Kelvin. You can see that it's immediately iterating, and your temperature distribution along the midway of the rectangular plate has now modified, and you get a new contour, right? So this essentially is basically the fundamentals of CFD, right? You basically have the geometry, which in this case is just a rectangle. Then you select the discretized equations. Then you select the equations that you want to solve, which in this case is just a 2D heat conduction equation. And then you mesh the geometry, which we are luckily able to do because of Microsoft Excel, which is already a cell-based software program. And then we provide boundary conditions, initial conditions, and we iterate. You can see that it takes a certain amount of time for the solution to change. And a good way to look at that is, if I set this back to 300, you will see that the graph continuously changes, and after some point, the graph stops changing, but the numbers are still changing, right? This is essentially saying that the results are converging, and that's a very good indicator. So for example, if I change this back to something like 800, you can see that the graph changes, but then at some point it stops changing, but the solver is still trying to solve it to a higher value of accuracy, right? And this is where things like residual and things like iterations come into play. But overall, it doesn't matter how complex of a model you take and simulate, all these fundamental concepts have to be followed in that simulation as well, right? It doesn't matter if you're simulating a battery pack with thousands of cells. It doesn't matter if you're simulating a fighter jet. The fundamental principles behind performing computational fluid dynamic analysis is exactly the same. You need the geometry, you need to mesh it, you need to select the governing equations, you need to provide the initial conditions, boundary conditions, solve it, and then finally post-process it. Alright, with that I would like to conclude this video. I hope through this video you learned the fundamentals of computational fluid dynamics. I'll see you guys in the next one. Bye.